Okay, so before I start, just let me make the usual disclaimer. You're going to hear a lot of things here about products from other companies, from other projects, from other consortiums. Not only I speak for myself, I hardly speak for myself even. I don't want to make any commitments in the name of the companies that are going to appear here. So just ignore the numbers and have some faith on what I'm going to tell you. Okay, so the Mont-Blanc approach is a European project funded under Framework Program 7 under the Exascale objective. So what we tried to put together is a European consortium, okay, made of companies which have their IP based in Europe, and try to develop a supercomputer from that technology based on the strength that we have in Europe, which is not HPC, which is embedded computing. Okay. One of the challenges, one of the big challenges of Exascale that everybody agrees with is energy consumption. And what most people will also agree with is that embedded computers tend to be more energy efficient than supercomputers. So can we get the best of both? And we'll see how the story gets together. So first, I'm going to go quickly, probably, through a bit of history of supercomputers. Let's see how supercomputers have evolved over time. And then I'll try to point out what we think is the natural next step in the architecture of computers. And we can sort of try to see if it makes sense to build a supercomputer from embedded processors, the ones that we have in our pockets. Okay, and then, well, we'll see what BSC thinks could be a future and what the Mont-Blanc system could look like. So, well, in the beginning, everything was dark and somebody said, turn on the light, but then sometime after that, there were supercomputers. They were the only computers. I mean, in the beginning, every computer was a supercomputer. There were only a handful of them. Somebody said that there was a worldwide market for about 20 computers. Okay, so all of them were supercomputers. They were built to order, they were incredibly expensive, and the aim was to crunch numbers. Okay, make computations, ballistic trajectories, and so on. Okay, the architecture of the time was vector computing. The programming paradigm was data parallelism. And there, the start of the time, control data convex, all of the computers over that time, Cray 1, 160 megaflops, Cray XMP, 800 megaflops, 2 gigaflops. Well, I mean, my cell phone would have been the #1 supercomputer of that time. So, what comes next? Microprocessors. CMOS technology starts coming into the picture. So, commodity computers, PCs, workstations, they start getting into the market. Here we can see a comparison of the floating point performance of our vector supercomputers and the microprocessors that were appearing in the market at that time. This is a log scale. Okay, so we're talking about processors that were about 10 times slower than the vector processors. But they were 100 times cheaper, and they took a lot less power. They were very small. So you could integrate a lot of them in the same amount of space, get competitive performance, save a lot of money. Well, I mean, sort of what happened? Well, I could continue this green line all the way up until 2012, but this red line sort of stops there. Essentially, microprocessors killed the vector processors. Okay, there was no market for them, there was no economics behind them to keep them alive. And, well, essentially, commodity supercomputers took over vector supercomputers. The ASCII red, the ASCII white, built with Intel Pentiums, with IBM Power 3 processors. Commodity, workstation type, PC class processors. Just put a lot of them together. The big change was the programming paradigm. It's no longer data level parallelism, it's MPI. Okay, clusters take over the world. And, well, clusters built with commodity components, specialized interconnection networks, specialized cluster software. And then at some point, I had to put a picture of Mare Nostrum, sorry. At some point, that's in 2004, commodity takes over completely. It's not just commodity hardware, it's commodity software. Mare Nostrum, biggest cluster running Linux, number 4 in the top 500 when it started operating. It's being decommissioned next week. So Linux operating system, open source compilers, open source MPI libraries. Yeah, you still have a mininet interconnect, but I mean, that's it. Commodity took over. Why? Because it's cheaper, because it's easier. So what's the next step? If I look at the commodity food chain, HPC is in the top, built to order, very few of them, extreme performance, extreme price. Servers, bigger market, still expensive. Desktop computers, these are the ones driving most of the machines in the top 500 actually. You change the enclosure, you put a lot of them together, put an InfiniBand interconnect, boom, you have a supercomputer. Let's look at the mobile space. If you add up all of the processors in the top 500 list, that's 13.5 million processors. Well, 27 million tablets sold in only 1 quarter last year. 100 million phones sold in only 1 quarter last year. Each one of those phones has not just one, probably more than one processor in there with floating point capability. Actually, my cell phone, which is sitting over there, has 6 gigaflops of peak double precision performance. Quite respectable, I must say. Would have been in the top 500 list all over the time until the 80s. So, well, why does that happen? Embedded processors didn't care about floating point computation because they didn't need it. But things are changing. New wireless protocols, 5th generation wireless communication requires floating point computation. Video algorithms require floating point computation. So the embedded space is implementing floating point units. All of these embedded processors have gone from 0 to 1 operation per cycle, 4 operations per cycle. The next ARM instruction set architecture coming up in a couple of years already has vector instructions with double precision capabilities, 8 operations per cycle. So from 0 to state of the art in a handful of years. They do have a huge advantage. All of the HPC guys, all of the server guys have been chopping the jungle ahead of them. Now they have a clear path. They know how it's done. So they can claim all of the wasted time and lost space in a very short time. So they have a much easier way to grow. They don't have to invent things. The others have already done that. So they're lagging behind, but they won't be lagging behind for that long. And they do have the experience when it comes to energy efficiency. HPC has been designed for performance over 40 years, and it's only in the last 5 that we have been actually concerned with power. These guys have been concerned with power from day 0. So they have been chopping the jungle when it comes to energy efficiency. So let's compare the energy efficiency of a high-performance HPC chip with a mobile chip. So this is the energy efficiency of IBM chips. This is the BlueGene P. This is the IBM cell. This is BlueGene Q. This is Nvidia GPUs. Okay, Kepler's not yet in the graph. Okay, and these are Intel CPUs with a big jump here on the Sandy Bridge. Okay, these are ARM embedded processors. And this is my own expectation for what the Cortex A15 could be. So there is potential. At least when you look at the energy efficiency, it makes sense. We do have an absolute performance problem. Okay? Each one of these BlueGene Q things packs 200 gigaflops in one chip. Okay? A quad-core A15 is only going to give you 32 gigaflops. And we're talking peak performance here. So, are the killer mobile processors coming? Well, we don't know. This is the price performance of a mobile chip, a desktop chip, and a server chip. So nowadays, a mobile chip is about 100 times cheaper than an HPC chip, and it's only about 10 times slower. Okay, because these guys already know all of the tricks that these ones have been playing. They can improve performance much faster than they are going to improve on their own side. So maybe in the future, the performance ratio is not going to be 1 to 10, and the cost ratio is most likely still going to be 1 to 100. Okay, and then there's an opportunity for taking a mobile chip, something that has been designed to go on a cell phone, and add a minimal set of features that make it HPC ready. It's going to increase the cost because there's a smaller method, but could potentially be somewhere here. So what is the sweet spot in that curve? And we believe in this Mont-Blanc project that the sweet spot could be on the bottom of that curve, on the low end. So this is based on public information that you can scrap from the web. The set of rumored features of the upcoming Samsung Exynos 5450. Okay, this is the successor of the one that goes in the Galaxy S3. So it's going to be a quad-core Cortex-A15. Okay, running at 2 gigahertz should give you about 32 gigaflops of peak performance, and an OpenCL-capable Mali T658 GPU, which, according to some sources, could provide something like 170 gigaflops of double precision performance. That's your 200 gigaflop chip, and it's designed to be in your pocket without burning your leg. Quite impressive. Okay, so is this going to kill HPC processors? Maybe. Well, legit question is if we're building BlueGene again. Okay, to some extent, yes. Okay, BlueGene has been chopping the wood in front of us. There's a clear path that we can follow. We're exploiting Pollock's rule. There's abundant parallelism. We're going to have tons of threads, tons of tasks to execute. So what you want to have is a lot of small processors, rather than having a few very big ones, very complex ones. But there's something else that we're going to try to play there. We're going to aim for heterogeneous computing. These mobile SoCs, all of them, have a lot of accelerators built in. They come with a GPU, they come with video and audio encoders and decoders, and they come with that. I mean, you cannot ask for the SoC without it, because it's going to be more expensive. Okay, so given that the accelerators are there, we're going to try to use them. So in that sense, the GPU comes for free with the SoC. It's a commodity processor. It's built to sell millions of smartphones. So the price is going to go down dramatically. Higher volume, many vendors, there's competition out there, there's many offerings. If there's competition, there's differences between the products, there's an opportunity for customization. Okay, looks attractive, much better than just having one vendor giving you something and telling you this is what you have to use. Okay, and these guys still have a lot of room for improvement. They don't have 512-bit SIMD registers for increasing data parallelism yet. They could easily build them in. It's just designing a functional unit, putting them there. The difficult part is doing an out-of-order superscalar pipeline. Okay, doing a functional unit is not that difficult. And we're trying to build on what European industry knows better, which is embedding stuff. So, does it really make much sense? So, this is a back-of-the-envelope comparison of a dual-socket Intel Sandy Bridge configuration with your InfiniBand FDR interconnect with an 8-socket ARM quad-core A15 implementation. So your Sandy Bridge is going to give you a total of 370 gigaflops of peak performance, 8 times 32, 256 gigaflops. Well, a bit less, but it's quite competitive. Big advantage is these guys have a special purpose interface. You have the 2 sockets, all of the processors in a single address space. Okay, it's shared memory programming. These guys don't. So you have 8 address spaces here. You're dealing with a cluster inside of a node instead of a shared memory space. 44 megabytes of on-chip cache. 16 megabytes, maybe 32 megabytes of on-chip cache. Okay, so we have to be more careful about locality. there's a smaller cache in here than there, okay, adding up the caches of all 8 sockets. Memory bandwidth, 136 gigabytes per second. I have a lot more memory channels actually. They're slower, so I only have 100 gigabytes per second of memory bandwidth. The ratio of gigaflops to bandwidth is actually fairly constant. And the big problem is I can exchange data between my Intel sockets at 64 gigabytes per second, because there's a special purpose interface for it. These guys, again, don't have it. So I'm going to have to exchange the data through my internode interconnection, which is only 1 gigabit per second. Okay? These are mobile things. They were never designed to talk to each other. So let's put accelerators in there. I mentioned GPU. So let's replace one of our Sandy bridges, put an Nvidia Tesla there, assume a Kepler GPU, 1.7 teraflops in 2 address spaces. Okay, so we're not the only ones having that problem now. 32 gigabytes per second between the GPU and the CPU through the PCI Express bus. Okay, and a lot of memory bandwidth. Okay, so these things come with the GPU as well. It's on the chip. I cannot do without it. So if I account for the GPU performance, it's also 1.6 teraflops, competitive. I have 16 address spaces, not 2. Okay, even if the GPU is on the chip, it's physically sharing the memory, but logically it's still on another address space. I have 12 gigabytes per second between the CPU and the GPU, because that's the memory bandwidth that I have. Okay, and 100 gigabytes per second of total memory bandwidth, which is about half of what I had there. Okay, so everything looks bad. A lot of address spaces, less cache, less memory bandwidth between the processor and the accelerator. So what's so good about it? That it's cheap and that it's more energy efficient. Okay, so it's worth at least taking a look. It doesn't look like it's product ready yet, but this is a research project. So there's no free lunch. We're going to build a prototype. We're fairly confident that we can make it work, and that there's a lot of challenges that we have to overcome. We need 2 times the number of cores for the same performance. We're going to have about half the on-chip cache as the regular offerings have. We're going to have to deal with 8 times more address spaces, and we have to deal with a very slow interconnection network. So locality is a big issue, strong scaling is a big issue, okay? Maybe a macho programmer can handle that, but how about the rest? We don't agree with that statement that the programming model is the 4th item on that list. Okay, programming model is the one that's going to enable Exascale. Either we change the way we program, or Exascale is just not going to happen, because there will not be enough programmers out there to justify the investment. So that's the key piece in the Mont-Blanc project. It's a very exciting architecture that I love to talk about, but the key piece of technology is the OmpSs programming model. Okay? The unit of parallelism that we're going to exploit is the task. So the low-level parallelism that Chappell was looking at. And we're going to rely on a smart runtime layer of software to handle all of the architecture complexity. Okay, our multiple address spaces just look like multiple functional units on a superscalar processor to the runtime system. You are giving me a data flow graph that connects the tasks together, and then I will do the scheduling based on which processor, on which address space is available. And the runtime system is also going to take care of transferring the data from one node to another, transparent to the user, overlapping data transfer with computation of other tasks. Okay, so this is what happens if you don't overlap. Either you compute or you communicate. This is what happens if you overlap. Not only you get faster execution time, you also become insensitive to the performance of your interconnection network, because there's usually much more computation than communication. Okay, hopefully. So based on this programming model, we can handle the problems of our architecture. We can handle the address spaces, we can handle the slow interconnect, we can exploit locality, we can exploit parallelism, so we can make a very complex architecture look simple enough to the programmer. So, well, altogether, it's a big challenge. Let's see how well we can do about it. This is the prototype roadmap that we've been building at BSc. So we started last year with an ARM multi-core cluster. Okay, we used this multi-core cluster to develop our entire system software stack to port the first version of our runtime system. This year, or maybe early next year, we will be enhancing this ARM cluster with a CUDA-capable GPU. Okay, so we're going already in heterogeneous computing. Let's see if our runtime system can not just handle the multi-core, it can handle also the GPU. And then around 2014, early 2014, we should deploy the Mont-Blanc prototype, which is not built on this ARM CUDA-capable system. It's already a single chip solution with the embedded accelerator in there. Okay, and it doesn't necessarily have to be an Nvidia GPU. And in addition, in the Mont-Blanc project, in addition to this prototype, which is going to be heavily limited by the silicon that's currently available in the market, okay, we don't have time or money to have our own SoC designed. We're going to design a next generation system that's not limited by what we currently see in the system. We're going to design our own SoC based on what we've seen in the market, and we're going to request those minimal set of features that would be necessary to overcome the limitations that we have here. Okay, for example, you have a booth out there where you have a quad-core ARM socket with multiple 10 gigabit links, okay, which would solve one of my problems, which is my 1 gigabit interface. So Mont-Blanc project has been drawing a lot of attention. It was a very popular project in supercomputing last year. It's been featured many times. It was highlighted by Eric Schmidt in the EC's Innovator Convention. Lots of press. We'll see. I mean, I don't know if you've ever heard the term of the hype curve. There's a technology trigger, so embedded processors now have double precision performance. They're very energy efficient. So the hype goes up. They're the solution for everything. They're going to fix all of the problems. Well, we'll see how far down we go on this side later on. So this is just a one-slide summary of the Mont-Blanc project. The goal is to develop a European exascale approach. Okay, with this project, there's a secondary goal that's not just to build an energy-efficient supercomputer, it's to make Europe an HPC provider, not just an HPC client, as we are today. And we want to do it based on power-efficient technology, embedded space, mobile space. We're going to deploy a first prototype, which is going to be limited by technology available in the market today. We're going to design a next-generation system that could be deployed sometime in 2017. Okay, and not just we're going to run loopback and benchmarks. We have a set of application developers which are porting their application to the OmpSs model to test if our runtime system can actually handle the problems that I've been claiming. Thank you.